Hello everyone, this is the presentation of our paper entitled Multi-Output Infinite Horizon Gaussian Process. This work has been done by researchers in Machine Learning and Control Systems Laboratory in Yonsei University, Seoul, South Korea. The state estimation of non-stationary dynamic systems, like human pedestrians, are essential for the robotics problem such as human-robot interaction. However, model-based approaches may not be able to deal with unmodeled and highly non-stationary situations. In contrast, data-driven approaches such as Gaussian process may perform well in a non-parametric manner, even with high nonlinearities. Recently, Gaussian process online learning such as an infinite horizon Gaussian process has shown effectiveness to cope with non-stationary dynamical random processes in learning hyperparameters online by reducing the cubic cost of the number of data point with order of m² per data point. However, infinite horizon Gaussian process is highly limited to the single output process. On the other hand, multi-output Gaussian process can handle the uncertain multivariate measurements while considering statistical correlations. The problem is the increasing computational cost for this. Therefore, extending the single-output infinite horizon Gaussian process to a multi-output infinite horizon Gaussian process is important to obtain a better prediction of multiple non-stationary signals. Our approach builds on the fact that the Gaussian process can be represented as a multivariate stochastic differential equation whose outputs can be considered as linear combinations of independent random processes. To derive a theoretically correct multi-output infinite horizon Gaussian process representation, we can consider the following high-order multivariate stochastic differential equation and its corresponding multi-output Gaussian process. Those multivariate stochastic differential equation can be rewritten as a canonical state space form as follows. F can be presented as the multivariate Gaussian random field with an input variable t. Then the multi-output covariance function is the inverse Fourier transform of S sub ff omega, which is the power spectral density of the output, f. By using this, we can find system coefficient matrices which corresponds to a existing kernel function. The Mattern kernel function can be an appropriate choice for non-periodic latent Gaussian processes since the Mattern kernels have an exact stochastic differential equation representation. From the power spectral density of the Mattern kernel, system coefficient matrices can be derived as follows. Now we can compute the Gaussian process predictions and predictive error covariances by Kalman filtering, since we found system coefficient matrices. The update and prediction step are given as follows. A discrete time system matrix F sub k for the Kalman filtering can be computed by the matrix exponential with a given time duration, delta t. Following the infinite horizon Gaussian process scheme, the steady-state Kalman filtering for a given local time window, delta t, can be considered. The stationary Kalman gain, k, can be computed as follows, and the stationary predictive covariance, p, can be acquired by solving the following discrete algebraic Riccati equation. Then the Gaussian process prediction, m, and the filter state covariance, p, are rewritten as follows. To cope with the non-stationary multivariate measurements, adaptive online learning of the time-varying hyperparameters can be considered. To construct an online learning method in the Bayesian framework, the posterior distribution should be updated when a new observation, y sub k, is collected. By the Bayes rule, the new posterior corresponding to the dataset, d sub k, can be divided into the previous posterior and the marginal likelihood given new observation, y sub k. The hyperparameter vector theta given the dataset, d sub k, can be obtained by maximizing the log posterior, where the log posterior function is given as follows. Efficient online learning can be achieved by replacing the previous posterior to a multivariate Gaussian distribution which parameterized by the mean, theta sub k-1 and covariance matrix, b sub k-1. This enables us to avoid using the entire dataset to compute the posterior. To approximate the posterior, we need to find the covariance matrix, B sub k-1. Since the approximated posterior has the quadratic form, B sub k-1 is equivalent to the inverse of the Hessian matrix of the previous posterior at the maximizer, theta sub k-1. A quasi-Newton method, such as BFGS, will be a good choice because it can find the approximate Hessian while updating the hyperparameters. If the dataset has a stationary distribution, the hyperparameter vector theta converges to the optimal value given entire dataset. For adaptive learning of the time-varying distributions, a discount factor, gamma, can be considered to give more weight to the new observation. We demonstrated the effectiveness of our approach with synthetic data benchmark. We generated two sinusoidal signal measurements, Y1 and Y2 as follows. The measurements of one channel are corrupted with a higher level of noise than the amplitude of the sine wave, making it difficult to determine periodicity. The blue solid lines are the original sinusoidal signals, and the black dotted lines are the GP predictions. As shown in figures, our approach detects the original signal in noisy situations, while two independent single-output IHGPs cannot detect the periodic pattern of the original signal. Since predicting the collective motion of a group of pedestrians is important for social robotics, we aim to show that our approach is able to predict the trajectories of pedestrians while considering the cross-correlations between them. To demonstrate our approach, the CITR dataset is used, which contains the top-view trajectories of various scenarios in the crowded university campus. To show the usefulness of the online learning of the cross-correlation coefficients, two scenarios in the CITR dataset is considered. The first scenario is the backward interaction scenario. Pedestrians split and merge to avoid a vehicle while moving in the same direction. The second scenario is the bidirectional normal driving scenario, where two groups of pedestrians pass by while moving in opposite directions. In order to measure the cross-correlations between pedestrians, following MOGP can be considered. The position vector P is defined as follows. Then the cross-correlations between pedestrians are computed from the cross-covariance matrix, sigma sub f, which can be estimated by learning the time-varying cross-correlation hyperparameter. Since the cross-correlations between two pedestrian positions p sub j and p sub k are vectors, a general cross-correlation coefficient for directional data should be considered. A general cross-correlation coefficient ρ sub jk between p sub j and p sub k can be computed as follows. This is the experiment video of two scenarios. The green and cyan lines indicates the predicted trajectories of the pedestrians, and the blue and red solid lines connecting pedestrians indicates the cross-correlations between pedestrians. The clearer and thicker the line, the stronger the correlation. The estimated correlation coefficients enables us to distinguish the two groups. Following figures are results of MOIHGP prediction using bidirectional normal driving case in CITR dataset. A is the prediction of the trajectories of the pedestrians and cross-correlations between the pedestrians. Triangle marks, the dotted lines, and the dashed lines indicate the positions and the headings of the pedestrians, the trajectories, and the cross-correlations between pedestrians of the other groups, respectively. The blue solid lines and the green solid lines indicate the cross-correlations between the groups with the blue markers and the green markers, respectively. The thickness and transparency of solid lines and dashed lines indicate the level of cross-correlations. B is the estimated time-varying cross-correlation coefficients ρ. The solid lines and the dashed lines are the cross-correlation coefficients between pedestrians of the same groups, and is the cross-correlation coefficients between pedestrians of the other groups, respectively. Learning the cross-correlations between the outputs also can be effective in the prediction of the outputs by taking into account the cross-correlations between outputs, especially the measurement of observations on specific channels that are occluded. To validate these effectiveness in the prediction of the outputs with the occluded measurement scenarios, 100 times of MC experiments were performed with randomly occluded measurements. The table summarizes the results showing with prediction errors of the IHGP, the MOGP with the fully independent training conditional approximation, and the proposed approach. In the experiments with the randomly occluded measurements, the prediction errors of the proposed approach are nearly 50% and 85% of the IHGPs and FITCs, respectively. In this study, we propose an MOIHGP that generalizes the single output IHGP to deal with multiple outputs for better prediction. By considering cross-correlations between multiple outputs in a Bayesian way, our approach could produce a better prediction for cases with high correlations and measurement noises and cases with the presence of occlusions. Moreover, online learning has been improved for better robustness compared to the IHGP via an empirical Bayesian way.